Okay, today we're going to look at takt time, cycle time, throughput, capacity, bottlenecks, a lot of different terminology, all related to some analytical techniques to help you determine, do you have enough resources, enough capacity in order to meet the given demand? Also to help you determine, where's your bottleneck? What's keeping your operation from moving faster than it's currently moving? So just definitions, a couple definitions here. Takt time is our available time divided by our demand. It tells us how fast we need to operate to keep up with given demand. Takt time is dictated by how many hours you're open and how many units your customers are buying or how many customers you have. It really has nothing to do with how fast your operation can run. Takt time tells you how fast it needs to run. How fast it can run is what we call cycle time. It's the elapsed time from starting a process to completing a process. Sometimes we'll see cycle time for individual steps in a process, sometimes cycle time for the entire process as a whole. It tells us how fast we actually run. And we can kind of play around with cycle time and available time and tell us throughput. Throughput is how much we actually produce in a given time period. So we're going to take our available time and divide that by a cycle time. So kind of how many hours are we up and running divided by how fast do we produce or process customers. Let's look at an example here. Available time in this example, we've got an 8-hour shift, 60 minutes an hour, so 480 minutes, but you can see that we subtract out some allowances, things like the fact that we know that just because we pay people for 8 hours, they don't actually work 8 hours. They take lunches, they take breaks. It takes time to get started in the morning. It takes time to clean up or kind of wrap up at the end of the shift. There's some personal time when you're there but you're not actually working. So maybe a more realistic number is 360 minutes are available during a shift. And in this example, we need to produce 20 orders every shift. So we got 360 minutes available. We need to produce 20 orders. So every 18 minutes, we need to produce an order. Now what we want to do with takt time and cycle time information is we'd like to get that onto a process map. We already did some process mapping earlier in the semester. So these two tools are going to work very well together with one another. And I have an example where that's been done. Here's a process map. You probably recognize the process map from the work we did before. It's a barbecue process map. Just kind of work through the steps, obtain information. So we have a step where they're obtaining information about the barbecue orders. This isn't a retail operation. This is a large processing facility. Once they get the information about the order, they got to decide, is it pulled meat or is it sliced meat? If it's pulled meat, it follows this top process. If it's sliced meat, it follows the bottom process. You can see that the steps are the same between the two processes, but the amount of time that it takes for each step is a little bit different. So we got a mixing step here in the pulled process. Mixing takes 30 minutes, proofing takes 25 minutes, cooking takes 64 minutes, packing takes 27 minutes. And similar on the sliced meats, but a little bit different time. And then we want to fill in how many stations do we have, or we might think of this as people. How many people do we have doing each one of these operations? So taking an order, we have one person, mixing one, proofing one, cooking 2 stations, packing 1, and we'll see what that 2 stations does when we start thinking about throughput. You can see down on the sliced process, 1 station, 2 stations, but here we have 2 stations. So packing for the pulled process only had 1 station, packing for the sliced process had 2 stations. We need to think about, well, how much can be produced with this process. So we need to go to this throughput calculation, the available time divided by our cycle time. Available time, like we talked about a minute ago, we're going to use 360 minutes available during every shift. But that's 360 minutes available for every person that's there. So when we look at this first station that has 1 person or 1 station obtaining information, 360 minutes divided by 7.5 minutes, it's our available time divided by our cycle time, tells us that we can process 48 units per shift, or 48 orders every shift through that station. Then those orders kind of split up here, and we'll start looking at, well, how much can we mix through the pulled station? Again, 1 station, 360 minutes available divided by 30-minute cycle time. So this station can process 12 units or 12 orders every shift. Look down here at cooking, a little bit different. calculation. Our available time is a number of minutes per shift, so we've already said that's 360 minutes every shift, times the number of stations, so it's times 2 stations. So we have 360 minutes times 2 stations, so we really have 720 minutes worth of processing time there, and we're still going to divide by the cycle time of 64. That's going to tell us we can process 11.25 orders or 11.25 units per shift. We're going to do that for all the different steps in our process, and then we're going to come back and we're going to find out where's our bottleneck, where are our slowest steps in the process. And probably pretty obvious to see, cooking in the pulled meat process is the slowest operation. We can only process 11.25 units per shift. All the other steps in the process can run faster than that. In the sliced operation, similar, but now mixing is our bottleneck, 14.4 units per shift, where all the other steps could run faster than that. So now you want to know, is that fast enough? Well, that depends on what the demand is. So now we got to get our takt time and our demand put into this process map to figure out, is this fast enough? Maybe this is fast enough. If we only need 10 orders per shift on the pulled line, and we only needed 14 orders per shift on the slice line, then this would be fast enough. Even though you have a bottleneck, it's faster than your demand. So we need to know what the demand actually is. And here we have our demand. Demand for the pulled meat is 11 units per shift. Demand for sliced meat is 17 units per shift. So let's see what that's going to tell us. All of the orders, whether they're pulled or sliced, go through the obtain information step. So we need 28 units per shift. And just a second ago we said we can actually process 48 units per shift. So we're good there. And then the order split up here, and from data that the customer supplied us, of these 28 units per shift that's coming through, 11 units are pulled meat, 17 units are sliced meat. So we need 11 units per shift through each of these 4 pulled workstations, and we need 7 units per shift through each of these 4 sliced workstations. And when we look at our throughput, we can see right there, that was our bottleneck, 11.25 units per shift, but we only needed 11 units per shift. So on our pulled line, cooking, which has 2 stations, is our bottleneck. That is the slowest step in the process, but this station will meet the required output per shift. On our sliced station, we need to produce 17 units per shift. And we see right away we've got a problem here at mixing. That's our true bottleneck, only can produce 14.4 units per shift, and we need 17 units per shift. So that's a bottleneck and actually prevents us from meeting customer demand. But we also see down here at packing 16 units per shift. Although it's not the true bottleneck, it also won't meet customer demand. So we can see that we've got 2 workstations that we've got to do some work with. And we'll talk about later what we can do to balance out the workload, ways that we can increase capacity, but we can see that our pulled workstations have enough capacity to meet demand. Our sliced workstations do not have enough capacity, at least mixing station and packing station do not have enough capacity to meet the required demand. Our bottlenecks, again, cooking is the bottleneck on the pulled station. The bottleneck in the sliced station is the mixing operation.